Good morning. Welcome back to module 3 of fluid properties. So today we will be discussing on viscosity of fluid. So let me summarize what we discussed in module 2 of fluid properties. We discussed at length 4 parameters, namely mass density, specific weight, specific volume and specific gravity. We defined each of these items. We mentioned the units and also derived the dimensions of these parameters, and also discussed on the factors influencing mass density and specific weight and specific volume. We derived the relationship between mass density and specific weight, and also we worked out a few problems to understand better in depth these concepts. So today we will move into viscosity, the next property, the 5th property in fact. So how to define viscosity? So viscosity is the inherent resistance that is offered by the fluid itself to its free flow. See, as we discussed earlier in introduction, the fluid cannot resist any form of shear force or shear stress. So as long as the shear stress continues to act on the fluid will undergo continuous deformation. So only when the shear force is removed, the fluid will come back to rest or attain static equilibrium. So when the shear force continues to act, the fluid will continue to deform, so which gives the property of the fluid, that is to flow or to change shape. So here viscosity is the inherent resistance, that is of the fluid to flow from one point to another point. So how to understand this property better? Say for example, let us take a personality, he or she wants to come up in life. So what is the obstruction for him or her to come up in life? The obstruction is only the self-obstruction. That is, if they are negative in character and do not have a positive attitude towards life, then they will not come up, leave alone the external hurdles. So the first hurdle to come up in one's life is only he or she. So they must leave the negative attitudes within them and look positive towards the life or develop positivity in order to move on or improve upon. So the obstacle for one's coming up in life is only he or she, not anybody else. There is no external factor, we can say, involved. So if they have the urge, they have the determination to come up in life, then definitely they can come up. So here viscosity is the inherent property. So the fluid itself is offering resistance to its free flow. So it is a property by which the fluid offers resistance to the movement of one layer of fluid over the other layer of fluid. So if we assume that the fluid particles move in layers, one layer over the other layer, then one layer, that is the molecules or particles of fluid in one layer, offers resistance to the free movement of the other layer. So let us now list out the physical phenomena which are responsible for the property of viscosity. So one is the cohesion. So cohesion is the intermolecular attraction. So as we have already discussed that any fluid is composed of numerous molecules, and the molecules have got a spacing, intermolecular spacing, if they are closely packed, and then if the distance, the spacing is less. If they are widely spaced, the intermolecular spacing is more. So cohesion is because of the intermolecular attraction. And then the second property, the physical parameter which is responsible for viscosity, is the exchange of momentum. See, for flow to occur, there must be velocity. So what is momentum? Momentum is mass multiplied by velocity. So every molecule or particle has got a mass, so it moves with a velocity. So when you assume the fluid particles to move in layers, one layer over the other layer, then there is exchange of momentum taking place between the adjacent layers. So the physical phenomena which are responsible for the property of viscosity, that is the inherent resistance to its free flow, are cohesion and then exchange of molecular momentum, exchange of momentum between molecules of adjacent fluid layers. Okay, now we have to discuss in detail how these factors contribute to the viscosity, that is the inherent resistance of the fluid to flow from one place to another. Now let us assume that the fluid is considered to flow in layers with one layer of molecules over the other layer of molecules. Let us now discuss the effects of cohesion as well as the exchange of momentum between molecules of adjacent layers. So how they appear? They appear as shearing stresses. So shear force divided by area. So shearing stress, so shear stress is nothing but shear force, shear stress is equal to shear force, and what is the area over which the shear force acts. So these shearing stresses, they offer resistance to the free flow of fluid. Now we can discuss further these aspects and ultimately derive what is known as Newton's law of viscosity. So let us consider two plates which are placed parallel to one another as shown in the figure. This is the bottom plate, say, which is held stationary, that means it is not moving, and the upper plate which is moving. So the lower plate is stationary, the upper plate is moving, and they are kept or placed parallel to each other. And two large plates, the surface area of these plates is very large and the thickness is very, very small, let us assume. Let us assume the thickness of these two plates are very small and they have a very broad surface area. And in fact, I have blown up the vertical scale. In fact, when they are kept close to each other, this gap will not be visible. So I have just blown up the vertical scale so that there is a gap, right, in which the fluid can be present. And let the distance between the two plates be y, and the space between these two plates, that is y, is filled with a fluid. Because the lower plate is fixed, it is not moving, the upper plate can move. And again, these two plates are kept parallel to one another, and the upper plate moves with a velocity v under the action of the shear force F. The upper plate is subjected to a shear force, that is, which is acting parallel to the surface of the upper plate, and therefore this plate, the bottom of the upper plate, is developing a shear stress because this force is distributed over an area, that is area of bottom surface area of the upper plate, and the plate is subjected to a velocity, that is capital V, under the application of the shear force. Now please note, the shear force acts parallel to the surface area of the plate, that is the shear force is tangential to the surface of the upper plate, and the fluid particles in contact with the bottom surface, that is the fluid particles in contact with the bottom surface of the upper plate, will also move with the same velocity as that of the plate, that is capital V. Now if you take the fluid particles which are sticking to the top surface of the bottom plate, which is held stationary, so these particles, fluid particles, will not be moving. That is, the velocity of the fluid particles sticking on to the upper surface of the bottom plate will be 0. And let us assume that, so at here the velocity of fluid particles is 0, and here the velocity of fluid particles is capital V, which is the velocity of the plate, upper plate. Now, as the thickness or as the spacing between the two plates is very small, so let us assume that the velocity varies linearly with respect to y. The velocity varies linearly. So, at any distance small y from the bottom plate, let the velocity be small v. At any vertical distance small y from the bottom plate, let the velocity of the fluid particle that is moving in a particular layer be v. And let the change in velocity in an incremental distance, vertical distance dy by b dv. Okay. So, this is what I have put here, what we discussed. The shear force F acts parallel to the surface area of the upper plate. Fluid particles in contact with the bottom surface of the upper plate will also move with the same velocity v, while fluid particle is in contact with the top surface of the lower fixed plate would not move because it is stationary. So, zero velocity. Now, if the velocity of the upper plate is not too great and as the distance between the two plates is very small, it can be assumed that the variation in velocity in the space y between the two plates is linear, with zero velocity at the level of the lower fixed plate and velocity v at the level of the upper plate. So, let v be the velocity of fluid particles at any distance y from the lower fixed plate. The variation in v is uniform with the distance y from the lower plate. So, experiments have been conducted by scientists on variety of fluids, and it is observed that the shear stress to which the fluid particles adhering to the bottom surface of the upper plate is subjected to that is F by A. So, F is the shear force to which the upper plate is subjected to, and that is the shear force to which the fluid particle sticking on to the bottom surface of the upper plate is subjected to. Same shear stress is proportional to the ratio of the velocity of the moving flat plate, that is upper plate, and the distance y between the two parallel plates. So, the shear stress, that is say tau, which is F over A, is directly proportional to the ratio of the velocity v of the moving flat plate, upper moving flat plate, and the distance capital Y between the two parallel plates. So, from similar triangles, so again we will go back to the sketch. So, if you take this is one right angle triangle, the bigger triangle, and this is another triangle, smaller triangle, and then a third triangle also can be done. So, the bigger triangle wherein the base is capital V and the vertical part is capital Y, and then the other triangle wherein the base is small v, the vertical component is y, that is the distance we are considering, and then this triangle wherein the base is v plus dv and the vertical distance is y plus dy. So, from similar triangles, so the ratio v by y can be replaced by the velocity gradient dv by dy. So, this is a velocity gradient. So, the velocity gradient, what it represents? It represents the rate of angular deformation of the fluid, So, now we have replaced, that is F by A is directly proportional to V over Y. So, this V over Y has been replaced by dV by dy, that is the velocity gradient or the rate of angular deformation of the fluid. So, let us represent the shear stress F over A by the symbol tau. So, tau is proportional to the velocity gradient. Now, let us introduce a constant of proportionality, that is mu, and equation 2 becomes tau is equal to mu into dV over dy. So we have eliminated the constant of the proportionality by introducing the constant of proportionality mu is called mu. So this equation gives the shear stress between any two thin layers of flowing fluid. This equation is called the Newton's law of viscosity, and the constant of proportionality, that is mu, is called the coefficient of viscosity, or it is called the dynamic viscosity, or simply the viscosity of the fluid. So we can call mu by three names: coefficient of viscosity, or dynamic viscosity, or simply viscosity of the fluid. So from equation 3 we have mu is equal to tau over dV by dy. So this is an objective MCQ, multi-choice question. Newton's law of viscosity relates option A, intensity of pressure and rate of angular deformation. So this is ruled out. This is not correct, because we are not talking about anything regarding pressure. So this is not there. So this option is wrong. Then shear stress and rate of angular deformation. Shear stress, so tau is equal to mu multiplied by dV over dy. So we have shear stress and we have rate of angular deformation, or the velocity gradient. So Newton's, that is tau, is proportional to dV by dy. So this is okay. Now the third one, shear stress, viscosity and temperature. So shear stress is there, viscosity is there, we are not talking anything about the temperature. So this option is ruled out. Then viscosity and rate of angular deformation. So Newton's law of viscosity relates what? Tau and that is shear stress and rate of angular deformation, not viscosity and rate of angular deformation. So this option is also wrong. So the correct option is Newton's law of viscosity relates the shear stress and the rate of angular deformation. So this is the correct one. So based on the Newton's law of viscosity, let us now define the dynamic viscosity of the fluid. So if you take any fluid, the dynamic viscosity mu of the fluid is defined as the shear stress that is required, to produce unit rate of angular deformation. So this is called the rate of angular deformation. So how mu is defined? The dynamic viscosity, or the coefficient of viscosity, or viscosity of a fluid, is defined as the shear stress that is required to produce unit rate of angular deformation. So now let us derive the SI units of viscosity. So let us create a new white screen. So let me write, so tau is equal to mu multiplied by dV over dy. Now tau is the shear stress, shear force divided by the area over which the shear force is distributed. Now the SI unit of force is Newton. SI unit of force is Newton. SI unit of area is meter square. So Newton per meter square is SI units of shear stress. Now dV is what? Change in velocity. Change in velocity. So that is change in velocity means it is in meters per second. Dy, it is the incremental distance between adjacent layers. So this is in meters. So we have Newton per meter square is equivalent to, so we have to find out the units of mu multiplied by meter per second divided by meter. So this will be equivalent to Newton per meter square into meter second divided by meter. So you have Newton second per meter square. So mu has got units of Newton second per meter square. Newton second per meter square. The SI unit of shear stress is Newton per meter square. The SI units of velocity dV, that is change in velocity, dV is meter per second. The SI units of distance is meter, hence the SI unit of viscosity is Newton per meter square divided by meter per second by meter, you get Newton second per meter square. Let us derive the mass units of viscosity also. Now the mass unit of Newton, you should know, Newton is, we have already discussed in the previous module. So Newton can be expressed as kilogram mass meter per second square. So from what we have the relation gamma is equal to rho g, that is specific weight is equal to g times mass density. So gamma has Newton per units of Newton per meter cube. Mass density has got units of kilogram mass per meter cube. G has units of meter per second square. Therefore, Newton has got mass units of kilogram mass meter per second square. So we can replace Newton So let us again open a new white screen. So we have the force unit is Newton second per meter square, that is for mu. This is the force units. Now let us define the mass unit. So Newton can be expressed as kilogram mass into meter per second square into second per meter square. So Newton has been replaced by kilogram mass into meter per second square into second per meter square. So we have kilogram mass divided by meter second. So this is the mass units of viscosity. Mass unit of viscosity. So kilogram mass per meter per second. Kilogram mass per meter second. So these are the fundamental units. Viscosity, there is another unit that is called derived unit. It can also be expressed in terms of poise in honor of the scientist, the physicist Poise. So what is 1 poise? 1 poise is equal to 0.1 Newton second per meter square. 1 poise is 0.1 Newton second per meter square, or 1 Newton second per meter square will become 10 poise. And there is also an unit centipoise. 1 centipoise is 1/100th of a poise, that is 0.01 poise. 0.01 poise means it is 0.001 Newton second per meter square. 1 centipoise is equal to 0.001 Newton second per meter square. Okay. So an associated property of viscosity, there is kinematic viscosity. So kinematic viscosity of a fluid is defined as the ratio between viscosity of the fluid and mass density of the fluid. So kinematic viscosity, it is denoted by the symbol nu, nu, nu. Nu is equal to mu over rho, or mu divided by rho. So again, coming back to the SI units of viscosity, deriving the SI units of viscosity, mu, let us use the mass units. There is kilogram mass per meter second and rho kilogram mass per meter cube. So when you simplify this, you get meter square per second. So kinematic viscosity does not involve the the unit of mass or unit of force. So it is devoid of the unit of force or devoid of the unit of mass. So meter square per second. So that is why it is called kinematic viscosity. So the term kinematics means wherein it is a science which or the branch of physics where do not deal about the force. We are very much interested in the effect. We are not very much interested about in the cause for the particular effect. So kinematic viscosity, like viscosity, we are using poise. For kinematic viscosity, we use the unit called Stoke. So what is 1 Stoke? 1 Stoke is 1 centimeter square per second. Or if you want to express in meter square per second, it is 1 multiplied by 10 power minus 4 meter square per second. Like centipoise, here also we use 1 centistoke, which is 1/100th of a stoke, that is 0.01 stoke, or 0.01 centimeter square per second, or 0.01 into 10 power minus 4 meter square per second. So now let us discuss on the factors affecting dynamic viscosity of fluids. Again, fluids, you have liquids as well as gases. Now let us take gases. So gases, with increase in temperature, suppose the temperature of the gas increases, then the viscosity increases, while for liquids, with increase in temperature, viscosity decreases. Now you have contrasting effects. So let me again create a new screen, white screen discuss. Now what is defined? So you have gas on one side, you have a liquid on other side, some gas and some liquid. Now the gas is at a particular temperature, say T. Similarly, the liquid is also at a particular temperature. Now, the temperature of the gas is increased to T1. So, T1 is greater than T. Similarly, the liquid temperature is also, say, increased to T1. So, T1 is greater than T. Now, when the temperature of the gas is increased, what happens? We have already seen that the molecular mobility increases. Here also the molecular mobility increases. Now what happens here? When molecular mobility increases, the molecules come closer together. The molecules come closer together. So here the molecules are widely spaced compared to the original spacing. So here, so within unit volume, so what happens? The molecules are closely packed. So when they come closer together, what will happen? The resistance to flow will increase. So when the molecules come closer together, the resistance to flow increases, that means the viscosity increases. Whereas in the case of liquids, because of increased molecular mobility, the molecules are widely spaced. They go, and therefore what happens, the viscosity decreases. With increase in temperature, the viscosity decreases. The resistance to flow is decreasing because the molecules become widely spaced. So for gases with increase in temperature, viscosity increases, while for liquids with increase in temperature, viscosity decreases. So that's what I have explained, I have given here. Fundamentally different intermolecular characteristics. In case of liquids, viscosity is governed by cohesive forces. Cohesive forces, that is intermolecular attraction. So once the temperature of the liquid is increased, the molecular mobility increases, resulting in weakening the cohesive forces because they become widely packed, widely spaced. So this weakening of cohesion results, the force of attraction decreases. The weakening of cohesion, the decrease in force of attraction results in decreasing the viscosity. The liquid molecules have more freedom to get displaced, to move freely. Whereas in case of gases, the viscosity is governed again by the molecular activity. As the temperature of the gas is increased, the molecular activity increases, bringing more molecules in a given space together. So they become closely packed. So this increases the cohesion, the intermolecular attraction increases, and therefore the opportunity or the freedom to move freely gets restricted. That means the viscosity gets increased. So two MCQs based on the discussion we had just now. The viscosity of a gas decreases with increase in temperature. In fact, the viscosity of a gas increases with increase in temperature. So this is the correct option. At room temperature, the dynamic and kinematic viscosity of water are both greater than that of air, or both less than that of air, or respectively greater than that and less than that of air, or respectively less than and greater than that of air. So at room temperature, the dynamic and kinematic viscosity of water are respectively greater. So at room temperature, that is at the same temperature, you have air as well as water. The dynamic viscosity of water is greater than that of air, and kinematic viscosity is what? Mu divided by rho. As the mass density of water is much higher than the mass density of air, the kinematic viscosity of water is less than that of air. Okay, so this is the correct option. So now we have derived the Newton's law of viscosity. Now we will define what are Newtonian fluids. So Newtonian fluids. So Newtonian fluids are nothing but those fluids which obey Newton's law of viscosity. It is tau is equal to mu multiplied by dV over dy. So those fluids which obey this particular law, Newton's law of viscosity, they are called Newtonian fluids. So common examples are air, water, glycerin, kerosene, etc. So what is that? Suppose this equation is of the form y is equal to mx. Y is equal to mx, where y is the shear stress, x is the velocity gradient or the rate of angular deformation of the fluid, and m is the slope of the straight line. So this is an equation of a straight line passing through the origin. So what? Y is the shear stress, x is dV by dy. So for example, so x I am taking dV by dy, and here I am taking the shear stress. Suppose, say for example, I define a straight line which passes through the origin, and if the slope of this straight line, say dy by dx, that is m is equal to dy by dx. This is nothing but your mu. The slope of the straight line gives the dynamic viscosity of the fluid. So, for Newtonian fluids, there is a linear relationship between the shear stress and the resulting rate of angular deformation of fluid. So, the ratio between tau and dV by dy, which is the constant of proportionality mu, does not vary with the rate of deformation. So, mu is a constant. So, what are non-Newtonian fluids? So, the definition is very simple. Those fluids which do not obey Newton's law of viscosity, they are termed as non-Newtonian fluids. So, that means what? There is a non-linear relationship between the magnitude of the applied shear stress and the rate of angular deformation. That is, the ratio between the shear stress and the rate of angular deformation is not a constant and varies with the applied shear stress. Say, for example, it is like this. So, I have dV by dy along x-axis, the shear stress along y-axis. Say, for example, you may have a curve like this. So, the slope of the slope is not constant, it is varying from point to point. So, the ratio between tau and dV by dy, that is a variable. This is a variable from point to point. So, the viscosity is not a constant. So, this is an example. This is how a non-Newtonian fluid can be represented. The curve representing a non-Newtonian fluid. So, let us define now what a plastic substance is. A plastic substance is again a non-Newtonian fluid in which the initial yield stress has to be overcome to cause a continuous deformation. So, how it will be like that? Say, for example, a plastic substance can be represented like this, by a curve like this. So, this is the initial yield stress, say tau naught, and this is the rate of angular deformation. So, an initial yield stress, that is the shear stress tau naught, has to be overcome in order to cause a continuous deformation. So, again the plastic substances can be divided into two classes as ideal plastic substance and then thixotropic substances. What is an ideal plastic substance? There is a definite yield stress which has to be overcome before the substance undergoes continuous deformation, and the ratio between the applied shear stress and rate of angular deformation is a constant. It can be like this. So, this is also a non-Newtonian fluid. So, it will be like this. Say, for example, tau is equal to tau naught plus mu into dV by dy. That is, this is the initial yield stress which has to be overcome before the substance undergoes continuous deformation, and the ratio between the applied shear stress and the rate of angular deformation is a constant. Afterwards, it is a constant. It follows a straight line. It is linear. Whereas in case of a thixotropic substance, it has got a non-linear relationship like this. There is a non-linear relationship between the applied shear stress and the rate of angular deformation. This example is printer's ink. So, this is in summary the complete figure. So, the velocity gradient is taken along the x-axis, the shear stress is taken along the y-axis. This is the Newtonian fluid wherein the ratio between the shear stress and the velocity gradient is constant, the viscosity is constant. So, non-Newtonian fluid is the ratio is not constant. Then this is an ideal plastic substance, ideal plastic, wherein you have to overcome an yield stress tau naught, and then the ratio becomes constant. That is, the ratio between the applied stress and the velocity gradient is constant. Then thixotropic, you have to overcome this shear stress, and beyond that the ratio is not a constant. It is called thixotropic. So now let us define what an ideal fluid is. We have already defined in module 1 what is the difference between an ideal fluid and a real fluid. So an ideal fluid is the one which has zero viscosity. That means the ratio between the shear stress and the rate of deformation is 0. That is, this quantity tau divided by dV over dy is equal to 0. Or in other words, the shear stress is always 0. This is always 0, regardless of the rate of deformation of the fluid motion. Okay. So this is again another MCQ. Let us consider the following fluids: blood, glycerin, molasses, slurry of clay in water, and then kerosene. Among these, the non-Newton fluids would include 2, 4 and 5. So glycerin is a Newtonian fluid, so this option is wrong. Kerosene again is a Newtonian fluid, so 2, 4 and 5, this option is wrong. So this is also wrong because glycerin is a Newtonian fluid. So we have to tell what are the non-Newtonian fluids. 1, 4 and 5. So 5 again is a Newtonian fluid, so this option is also wrong. So we are using the process of elimination. We need not know very much which fluid is which type of fluid, but therefore this option is the best option, that is 1, 3 and 4. That is blood, molasses and slurry of clay in water. They belong to the non-Newtonian fluids category. So now, we have come to the end of module 3. So I will summarize what we discussed today. We discussed only one property, that is viscosity. So we defined what viscosity is, the physical phenomena responsible for the viscosity of a fluid. We derived the mass units as well as force units. Then we discussed on the factors affecting viscosity, how the temperature influences the viscosity of a gas, how the temperature influences the viscosity of a liquid, and then we derived the Newton's law of viscosity and also defined what are Newtonian fluids, non-Newtonian fluids, then what is a plastic substance, what is a thixotropic substance, and then we also discussed about, and also I presented to you some multi-choice questions based on this particular parameter. So thank you. Let us meet in module 4, wherein I will be working out a few problems involving viscosity. So thank you. Have a good day.